So Christophe Petite is at the UC Louvain, and he's going to talk about the complexity of ECDLP for composite fields.
Hi everybody. Thank you very much to the organizer for inviting me. It's a pleasure to be here and an honor. So today I'm going to talk about the complexity of ECDLP for composite fields, especially binary fields. So where is it? Hmm? Yeah? Down? Okay, sorry. So, yeah, as you know, the discrete logarithm problem is the following one. You're given a group G, a cyclic group. You're given an element in that group, a generator, and you're given another element that's H, and you want to find some integer k such that H is equal to J to the k. So it has many, many applications in cryptography, including Diffie-Hellman key exchange, algebra encryption, digital signature, and so on. So, yeah. So in cryptography, we take the assumption that the DLP is hard, at least for certain groups. So typically, we use a multiplicative group of finite fields. We use elliptic curves, and we use Jacobians of hyperelliptic curves. So, but of course we take the assumption, we don't really know whether it's true or not, it's just an assumption. So, and we may wonder how hard it is actually. So, the answer seems to depend on the group. So, we do have sub-exponential algorithm for finite fields and for hyperelliptic curves. And it's also known that some particular curves, elliptic curves, are weak. I don't know. Can you hear me like that? I prefer. No? Okay. So never mind. So that means that in practice, if you want some security level, you have to take larger parameters for DLP than for ECDLP. So more or less 160 bits for like 1,000 or 2,000 bits DLP. So in this talk, I'm going to talk about elliptic curve discrete logarithm problem for binary curves. And so this is quite important because it includes 10 out of the 15 curves that were standardized by NIST. The complexity was until recently thought to be exponential in n. But I will argue that the complexity might actually be this. So it might be sub-exponential with an exponent 2/3 here. So compared to DLP, in DLP you have 1/3. Here it's not as good, but it's still sub-exponential. Okay. So here's the outline of my talk. So the first part will be to reduce ECDLP problem to some particular polynomial systems. Okay. Then I will give you some general background on how to solve polynomial systems, especially with a focus on cryptography problems. The third part would be to dedicate it to a special kind of polynomial systems that I call arising from a Veidesen. It will be clear why later. And after getting complexity estimation for this problem, I will go back to ECDLP and get the main result. Okay, so let's start with ECDLP. So the elliptic curve discrete logarithm problem again. So you're given some curve over a finite field k. You're given some element p, some point of the curve, and another point q, and you want to find some k such that q is equal to k times p. For binary curves, you have a finite field with characteristic 2 here, and curves have this form here, where A6 must be different than A6 must be different than 0. And well, the curve is called a Colbit's curve if it belongs to F2. So we wonder how hard is this problem for binary curves. So first of all, there are some generic attacks that apply for any groups. So for example, exhaustive search, baby step, giant step, polar Hur, Polyk-Hellman. In general, for elliptic curves, it's it has been believed that there is no better algorithm than those, except for maybe some very special curves. And as a result of that, the key size that you take are much smaller for elliptic curves than, let's say, DLP or factoring. So there is another range of attacks for elliptic curve discrete logarithm problem that kind of transfer the ECDLP problem to another DLP problem in another group. So for example, so there is the Menezes-Okamoto-Venstone reduction that transfer the ECDLP to some DLP over an extension of K. Sorry, here. There is also, well, actually a polynomial time algorithm if you take very special curves that are called anomalous curves. And there has been a bunch of work along what's called veil descent, where you transfer the ECDLP to some hyper elliptic curve problem. So all those attacks only work for specific families of elliptic curves that are not the ones that we would like to use in practice. Okay, in this talk I will focus on one kind of attack that's called index calculus. It's actually a very generic attack for DLP problems. So it works as follows. First of all, you define some factor basis F, which is a set of elements of the set, of the group, sorry. And the second step is to find relations. So a relation is a formal sum like that includes the 2 points P and Q. So you're looking for the discrete logarithm of Q with respect to P. And that includes some point Pj here that are in the factor basis. So in the relation search step, you will have to find roughly size of F relations. And finally, when you have all those relations, you can perform sparse linear algebra on the relations in order to find a relation of this type. And once you have that, you just take B minus A times A to get the solution. So it works for DLP, for hyperelliptic curves, and so on. But here I haven't defined everything. So you still have to define like this set F. And in particular, you have to define it such that you can have, let's say, efficient algorithm for doing this. And well, of course, we'll have to balance the different steps. So usually well, this step is trivial, but you will balance relation search with linear algebra. Okay. So to give an example of index calculus for DLP, so you given G and H belonging to F to the N, and you want to find some K such that H equal to G to the K, sorry. So you take as a factor basis all the set of small primes. So primes here are really irreducible polynomials F, such that the degree, because you want them to be small, you say the degree must be smaller than some bound B. And for the relation search, one thing you could do is just to take random A and B. You compute random, you compute this product J to the A times H to the B, and you hope that this product can be decomposed into elements from this set. Okay? So, well, you can factor using Berlecamp's algorithm quite efficiently. So if all the factors belong to the set, the factor basis set, then you have a relation. Otherwise, you just try again. Okay. So if you take B roughly n over, sorry, that's wrong. Sorry, that's true. So n over n to the power 1/2, then you get some sub-exponential complexity. There are improvements of this algorithm, of course. So index calculus has been very successful among the years. So first of all, for finite fields, so there has been the algorithm of Edelman, then Coppersmith's other algorithm. So all those algorithms have a complexity sub-exponential with an exponent here roughly 1/3. And we also have been able to, the community has been able to adapt those attacks to hyperelliptic curves when the genus tends to infinity. But for elliptic curves, it has been a big open problem, and there was actually no algorithm at all until 2005. So one of the main difficulty in adapting this index calculus approach to elliptic curves was how to define the factor basis and how to find relations. So for finite fields, you have a natural definition that consists of the small primes. So every element factors uniquely as a product of the small primes of primes, sorry. And there is a reasonable probability that random elements are going to be smooth. So for elliptic curves, we will also need something similar. So we'll need a definition of small elements, and we'll need an algorithm to decompose general elements into, let's say, potentially small elements. Okay, so the first partial solution to this problem was given by SEMAF. Okay, a key ingredient to adapt index calculus to elliptic curves is what's called summation polynomials. So those polynomials basically relate the x-coordinates of points on the curve that sum to 0. Okay, so more formally, the polynomial SR, well, it's a multivariate polynomial in R variables. It's equal to 0 if and only if there exist points on the curve xi, yi, such that those sum up to the point at infinity. Okay, so SEMAF showed that well, first of all, you can compute those polynomials. There is a recursive formula for that. So you can just write S2 and S3, and then you have this recursion where you can compute SR from SR minus K and SK plus 2, for example. Okay. And another property that he proved that we will use later is that this summation polynomial, that's also called SEMAF polynomial, has degree 2 to the R minus 2 in every of those variables. Okay. And well, of course, there is a symmetric set of solutions to this polynomial, just because well, the elliptic curve is an abelian group. Okay. So the idea of SEMAF was to do index calculus like this. So you define the factor basis FV as the set of points on the curve, such that the x-coordinate belongs to some V, where V is a subset of K. Okay. So once you do that, the relation search problem amounts to the following. So for each, so you generate random AI and BI just as before. You compute AIP plus BIQ, and then you want to decompose this point into a sum of points in the factor basis, right? So this amounts to the following problem. By definition of the SEMAF polynomial, you will have to solve this polynomial with the additional constraint that all the solution belongs to this set V. Okay, and once you have that, you find the corresponding y-axis coordinates. So SEMAF's observation was really that you can reduce ECDLP to solving those polynomials with the constraints. Okay, but well, it remains to define the V such that relation search will be feasible. So for the final field, prime fields, SEMAF proposed to use, similarly to finite fields, he proposed to use V as the set of elements smaller than some bound B. But unfortunately for him, he couldn't solve summation polynomials in that case. So later, both Gaudry and Diem came out with a similar algorithm for, well, a similar ID, but this time for an extension field, FQ to the N. And they proposed in that case to use V equal to FQ. So the subfield, which is, yeah, it's a subset, of course, of this. So in Gaudry's attack, the algorithm is faster than generic ones for any n smaller, larger than 3, but it's still exponential. Okay, and Dean made a similar algorithm where he let Q and N increase like simultaneously, and he showed that in that case you get some sub-exponential complexity. But well, the idea in both cases was to solve the semi-F polynomial, the summation polynomials, by applying a veil descent on the polynomials. So by doing this, you will reduce like the solving of the equation to solving a polynomial system of equations. So let's go into more details. So again, finding a relation amount to solving summation polynomials with this time the constraint that xj belongs to the subfield. And well, if you see fq to the n as a vector space over fq, you can also see the polynomial equation s n plus 1 equals 0 as a system of polynomial equation over the subfield, right? So you get a system and you solve the system, okay? So using like generic complexity results about solving polynomial systems, both Godfrey and Dim get the complexity of their attacks. So well, it's important to note maybe that the system becomes harder to solve for larger n. So in particular, if you take a binary field f2 to the n with n prime, the only choice that you have there is to use fq equals to f2. Okay, and so the system is quite large. It has n equation, and so the attack doesn't work in that case. Okay, so the next step was done by Dim again. So in the case where n is prime, instead of taking v equals to a subfield, so there is only one subfield, which is f2, he suggested to choose v as a vector subspace of f2 to the n. Okay, so you fix some n prime smaller than n, of course, and some m, which is such that n times n primes is equal to n, more or less. Okay, so you define the vector subspace v of dimension n prime, and you define the factor basis as the like before, as the points on the curve such that the x coordinate belongs to this subspace v. Okay, so now the relation search amounts to like before you compute those random points, and you have to solve those polynomials such that the xi belongs to the subspace v. Okay, and linear algebra and so on. So we still have to solve those polynomials, right? So the technique that's used is called veil descent. Yeah, okay, I already talked about it. So you have to solve this polynomial with the constant. So defining a basis for v, v1 to vn prime, you also define binary variables g, xij belonging to f2 then, such that, well, they are in correspondence with the variable over f2 to the n, right? So xi is equal to sum of xij vj. And you just substitute the variables here in the semi-F polynomial here. So now you have to solve this equation, okay? And again, you see f2 to the n as a vector space over f2, and this gives you a system of polynomial equation over f2, okay? So the complexity of this algorithm, so first of all, you have to compute this semi-F polynomial, which is actually not a trivial task, but for small m it can be done. The complexity is roughly to the t1, where t1 is roughly m squared. And then, well, the main part maybe is to find the relations, right? So the total cost will be 2 to the t2, where t2 is equal to n prime plus log of the time to compute one relation, okay? N prime being because you need 2 to the n prime relations about. Okay, and finally, sparse linear algebra, you got 2 to the that's T3, such that, okay, T3 is that. That's just linear algebra cost. Okay, so our result is that when P is small, the systems that, this kind of systems arising from a very distant, are actually much easier to solve than random systems. Okay, and in particular, if you take some heuristic assumption that's common in algebraic cryptanalysis, I will come back to that. An assumption that's also validated by experiments for small parameters, then you can choose m and n prime in this algorithm such that, well, the algorithm has a complexity that's sub-exponential. That's the complexity there. Okay? Okay, so that finishes the first part. Let's now have some general background on how to solve polynomial systems of equation in general, in particular how we do that in cryptography. Okay, so algebraic cryptanalysis. Well, sorry, Thursday. So algebraic cryptanalysis is like a general way of general cryptanalysis method that consists in like reducing some problem to a system of multivariate polynomial equations, and then of course you solve those equations. So typically you will use if you consider generic polynomial systems of equation, in general they're hard to solve. Okay, but it turns out that in the system that appears in cryptanalysis setting, they're usually far from generic, and then they're easier to solve actually. Also systems are then usually solved with Grobner basis algorithm. Sorry, and there have been quite some success stories of these techniques. Most importantly, maybe HFE and variants of it, but also isomorphism of polynomials, some Macaulay variants, and yeah, also algebraic sectional attacks. Okay, so here is like general problem. We have a finite field K, and consider the ring of polynomials over over this field. We have n variables. We have m polynomials over the ring, and we want to solve the corresponding system here. Meaning we want to find variables xi, values for those variables such that all polynomials are 0. Okay. So if the polynomials were linear, then you can use Gaussian elimination. That's easy. But what about polynomial systems? So the main idea actually is to like reduce to Gaussian elimination. So you construct all the products starting from the polynomial fi. You construct products tj times fi, where tj is a monomial and the whole polynomial has degree smaller than d. Okay, so you construct all those products. You like consider them as a sum of monomial terms, and then you write all the coefficients in a big matrix that's called Macaulay matrix. And the Macaulay matrix basically has a row corresponding to each of those polynomials and a column corresponding to each monomial. So once you have, let's say, more rows than rows than columns, then you can do linear algebra and recover the solution. Okay. So the theory says that if D, so the size of the matrix, is large enough, then there are some linear combinations of the row such that the polynomials that you get have degree smaller. Okay, and again, if D is large enough, then you can perform linear algebra on MD, and you will get some, let's say, triangular, like Gaussian elimination, triangular system of equations that has the following form. So the last equation only depends on the last variable. So you can solve this using, for example, Berle-Kamp's algorithm. Then once you have the solution in xn, you just put it here and recover the value of xn minus 1, etc., etc. So that kind of system is actually called a Grobner basis for lexicographic ordering. So just to give you a formal definition, so Grobner basis, I'm given an ideal generated by some polynomials f1 to fm, and given some ordering of the monomials. A Grobner basis for this ordering is another basis, f1 prime up to fl prime prime, such that any element in the ideal, for any element there exists some of those elements here, such that the leading term of the element of the basis divides the leading term of f. Okay? So that definition implies that if you take any f, you can, sorry, there's no belonging to I here. Any f can be uniquely reduced by the Grobner basis, because you just consider the leading term, you divide by this polynomial, you take the remaining, etc., etc. So in particular, the problem that's called ideal membership problem, which is given f, does it belong to I? This problem becomes trivial once you're given a Grobner basis. Okay? So when it comes to algorithm, the first algorithm was given by Bush-Berger in his thesis in '85. The connection with linear algebra, the way I presented you, was really made by Lazare in '83. The best algorithm today are Fourier, F4 and F5. So since in this algorithm we don't know this maximal degree, the degree where we have to go, so basically what they do, they start with some degree, and then they do the linear algebra, and if it's not enough, they increase the degree, they put more polynomials, and they do linear algebra again. Okay, so so then, okay, F5 and F4 have some tricks to optimize to avoid some, for example, trivial reductions. So if you have two polynomials in your basis, f1 and f2, and multiply f1 by f2 and multiply f1 by f2, sorry, f1 by f2 and f2 by f1, then, well, clearly f1 minus f2, f1, f2 minus f2, f1 is 0. So when you write this matrix, that will correspond to like linear combination that leads you to rows that are just 0, that are useless, okay? And you can predict these useless rows. So basically what F5 is doing is preventing those rows to appear by avoiding some of the rows, okay? And in F4, the reductions are also parallelized. So the complexity of Grobner basis algorithm can really be estimated from cost of linear algebra on the largest Macaulay matrix that will appear during the computation. Okay, so therefore an important parameter is what's called the degree of regularity, which is the maximal degree of all the polynomials that you have computed. Okay, so given that degree, the number of monomials at the degree is roughly n to the d reg. Okay, so the total cost given the degree d reg can be estimated in time and memory just by linear algebra. So n to the w d reg and n to the 2 d reg, and if we just take w equal to 3, well, w is the linear algebra constant, so it's smaller than 3 and larger than 2. Okay, so of course, so this parameter is very important. So for random systems, we know we have like explicit formula that shows that tells that if you have n equations with degree d1 up to dn in n variables, so same number of equation and variables, the degree of regularity is roughly this, so roughly the sum of the degrees, let's say. Okay. Another thing that we know is that if you add more and more equations, the system becomes easier and easier to solve. Okay. So overdetermined systems have lower degrees of regularity. So if you can like model your system of equation in such a way that you have more equations, then usually it becomes easier to solve. Okay, so still a word about polynomial systems. If you are over finite fields, you take your system here, and you just add the field equation. Okay. We also have formulas for degrees of regularity of generic binary systems, for example. Okay, now let's come to another very important parameter, which is what can be called the first fold degree. So it's the lowest degree D, such that there will exist a non-trivial degree fold. What I mean by that is that you make linear combination, algebraic combination of the polynomials, such that the expected degree will be D, because all those terms will be of degree at most D, but the sum here has degree lower than D. Okay, so you would expect degree D, but you get something lower. Okay, and what I mean by non-trivial is roughly what I meant before when I discussed F5, is that if you have relations such that sum of the GIFI equals to 0, that's useless, and also because you're over the finite field FQ, this is also a useless relation. It's something that you know. Okay, so that's also the first fold degree is also a very important parameter. It turns out to be in practice, at least. It's so close to the degree of regularity that sometimes it has even been called degree of regularity in the literature. Okay, so for many classes of systems, it has been experimentally seen, and there are also some theoretical results supporting that the first fold degree is roughly equal to the degree of regularity. Okay, it's not true in general, but there is experimental evidence, at least for, let's say, random systems and also many crypto systems, including HFE and variance. So the intuition for this is that for these systems, at least, once you get a degree fold, you don't actually get only one, but there will actually be many degree folds. And so you get many lower degree polynomials that can in turn be combined to get even lower degree polynomials, and so on and so on. And finally, you will get linearization, the solution. Okay, so this assumption will be used in our analysis. Okay, so I will assume that the first fold degree is a good approximation of the degree of regularity. Okay, so I'm done with a general background on algebraic analysis. Now I will focus on a special kind of systems that I call polynomial systems arising from a variant. Okay, so well, be careful. There are like 4 parameters, but I will explain them now. So I'm working over a field. Well, this could be P as well. Let's say 2. So finite field F2 to the n. So n is the extension. There are n variables, and n prime is the size of some vector space V. Okay. T is somehow the degree of the polynomial. Okay. Actually, it's the polynomial is degree bounded by 2 to the t minus 1 in each of those variables. Okay. So total degree n times 2 to the t minus 1. Okay, so the problem I want to solve is to find xi belonging to v such that the polynomial is equal to 0. Okay, so I want to solve this polynomial, but with the additional constraint that the xi belongs to those subspace. Okay, so if v was equal to f2 to the n, the whole field, then that would be very easy to solve. You can fix random values for all the variables but one, and then use Berlekamp. Okay. Other remark is that I will assume that n times n prime is roughly n, such that well, if f is chosen randomly, at least I expect roughly one solution to this polynomial. Okay, so starting from that problem, I apply a Veldeston like before. So let v1 to vn prime be a basis for v, and let theta1 to theta n be a basis for f2 to the n over f2. Okay, I define binary variables xij such that xi, which is a variable over f2 to the n, is the sum of xij vj. I substitute that in the polynomial f here, and then I reduce modulo the field equation. So since xij belongs to f2, we know that xij square is equal to xij. So I reduce modulo this equation, and I get an equation over f2 to the n that I decompose in the basis theta 1 up to theta n. Okay, this gives me an equation that I write as follows. So this notation means like the one component of the veil descent of f. Well, it's actually with respect to a basis, but let's forget about it. So we get n equations in m times n prime variables xij. Okay. So when we will want to know like the complexity of solving these systems, the first thing that we will be wondering is what are the degrees of those equations. Okay. So just to get the intuition, let's suppose that we apply a veil descent to this polynomial, the monomial xi to e, where e is this number in binary. So we have, you can write xi as the sum of xij vj as before, and write the exponents here. So by linearity of squaring in f2, you write this as follow. Then xij square is equal to xij. So that's what you get here. And if you look at this, you will get polynomials here that have degree in the variables xij that's at most the number of those exponents that are equal to 1, right? So the degree of the veil descent here is the Hamming weight of E. All right? So if we generalize that, starting from the polynomial f that had degree at most 2 to the t minus 1 in every variable, we get that the veil descent component had degree at most t in every block of variables x, well, every block of variables corresponding to the different variables over f2, okay? f2 to the n. So the total degree is mt, but this degree can be decomposed into different blocks. Okay, so applications of this problem, well, you might have already guessed that I will apply this to a CMS polynomial, where the degree is 2 to the n minus 1 in every variable. But also you can apply this to a hidden field equation polynomial, where the degree was bounded by some d. Well, the system was a bit special, but well, we'll see that it doesn't matter so much actually. Another application is index calculus for f2 to the n. So, well, we know good index calculus algorithm like Cooper-Smith, but here we have a different algorithm with actually worse complexity, but okay, that's interesting. That case, we have degree 1 in each variable. And you can also apply this to a certain factorization problem in a non-abelian group. Well, that's less easy to see. But let's yeah, HFE. So the hidden field equation crypto system was a public key crypto system proposed by Batarin in 96. So there the private key is a polynomial f belonging to f2 to the n, over f2 to the n, sorry. The public key is somehow hidden, disguised version of its veil descent, okay? And the attacker only knows the disguised version and wants to solve the system. So some particularities of HFE with respect to like my general case is that well, the system is disguised. Well, this actually doesn't matter for the complexity because the hidden steps are just linear operations. Two other particularities. So we're in the monovariate case, m equals to 1. We only have one variable, and also, so these polynomials are very special. They have so they only have exponent here with Hamming weight 2. So the system that you get is a quadratic system. Okay. So HFE has been well studied, and we have a lot of results about it, we'll see that our analysis somehow generalize those results. Okay, so back to the general case. We had n equations over within m times n primes variables that were given by applying the values, so these components. And we know that if we could add more equations to the system, then we could accelerate its resolution, right? So can we find more equations? So the first idea that we had was the following. If f is equal to 0, then f squared is equal to 0. Okay? So far so good. But moreover, the Hamming weight of the exponents in f and f squared are the same. So that means that you won't only get new equation by applying a value on a square, but you will also get a new equation that have the same degree. So you keep with low degrees. That's good. Okay. Unfortunately, what you can show is the following. So if you just write f squared as, so that's the decomposition of f, then by linearity you can write this, you can put the exponent here, and since f, the value here is defined over f2, you can remove the squaring, sorry, then you write theta I square in the basis theta j, okay, and you like rearrange terms to get this, okay, and then you say that, okay, this is equal to the value of f squared. Okay, so by identifying terms, you see that the j component here is equal to a linear combination of the equation, the Valuson equation of f. Okay, so linear combination means that won't help, because in Gromner basis algorithm, all those equations will just be reduced by 0. Trivially, okay? So that ID doesn't help. So second ID, if 0 is equal to f, then, for example, x1 times f is also equal to 0, okay? So let's see what happens if you apply Valuson x1 times f. So here it is. So this time, x1f has degree bounded by 2 to the t in x1 and by 2 to the t minus 1 in the other variables. So the degree is still, because the Hamming weight here is always smaller than t, the degree is still a t in every different block. So that's good. And also, the equations that you get are not the same ones this time. Well, it's harder to show that they're not the same ones, but one intuition that you can get is that, well, if you decompose f in terms of a polynomial that doesn't include x1 here and x1 times another polynomial without x1, then x1 times f is equal to this. So, and this, so when you apply a Valuson to this, you get equations that are homogeneous in the block x1. So in particular, there can be a linear combination of the previous one. At least there can be the same ones. So you can apply the same ID with x2, x3, or x1 times x2, or even larger monomials. You might get equation with higher degrees, but still, I mean, not too high. Okay, so you get by this technique you will get many new low degree equations. Okay, which is supposed to help in the resolution. Okay, so let's see this new equation in another way. Okay, let's define a ijk such belonging to f2 such that theta I, theta j is equal to this. So you just write x1f in terms of the Valuson here, two Valusons. You get, then you decompose, you get this. You rearrange terms a little bit to see that the k component of the Valuson of x x1f can be written as follows. And again, grouping together all the terms in front of fj here, you get a polynomial here that has degree 1. Why does it have degree 1? Because the valence of x1 is degree 1, okay? So you apply a linear combination of polynomials of degree 1, you get a polynomial of degree 1, okay? So what does it mean? It means that the new equation that you got by applying a valence on x1f are actually algebraic combination of the original ones. So you can get them by like multiplying the original equation here by polynomials here, okay? But it's algebraic combination and not just linear combination. So it's not like before where they were just the same equations, okay? Actually, algebraic combination is exactly what Grabner basis algorithm will do. So those new equations that I've added explicitly will be recovered as well if you use standard Grabner basis algorithm, let's say blindly. Okay, you can of course add them, and you can get some complexity improvement. But if you don't do that, you will also get this equation anyway. Okay, so first full degree, we have that the valence of x1f is equal to this. Okay, so this is a polynomial of degree, well, those are polynomials of degree 1. This is polynomial of degree mt. And we have seen that this also have degree mt. Okay, whereas we would expect this to have degree 1 plus mt equals to mt plus 1. So we do have a degree full here, okay? It's not a trivial one. And so this shows that the first full degree in that case is slower than mt plus 1, which is essentially as small as it could be because we're starting with equation of degree mt, okay? Well, unless f is somehow degenerate. Okay, so if we heuristically assume that, like I said, that the first full degree is a good approximation of the degree of regularity, let's say in most cases for f randomly chosen and v also randomly chosen, then, well, sorry, again, this is kind of classical assumption in every paper in algebraic analysis. There is experimental evidence for, let's say, random systems and many systems, many crypto systems, including HFE, which may appear as like a particular case, and there is even confusion in the literature. So if you take this assumption, you straightforwardly get that the degree of regularity is roughly equal to mt plus 1. Instead of, for generic systems, roughly n times that. Okay, so it's much lower than for generic systems. Okay, here are some experimental results. So in these results, I use Magma, and so I chose a random polynomial, random subspace, and computed the, computed the valence and applied like a Magma-Grabner algorithm, and I observed the maximal degree appearing, which is here, okay? Here in this column you see mt plus 1, which is the point I'm trying to make, right? The value that I would like to say that is the correct one, or more a good approximation, sorry. So you see that it's not that bad, right? Especially if you think that for generic system it will be n times that, okay? So in this you have only polynomials of degree for t equal to 1, more data for t equals to 2, 3, or 4 also shows that, well, it seems to be like reasonable. Unfortunately, we can't go very far in this computation, mostly because of memory. So here I was close to the maximum memory I had, so I couldn't check the assumption for larger parameters, unfortunately. Okay. So back to the complexity of analysis. If we take this assumption, we have degree reg equal to mt plus 1. So time and memory are bounded by nw dreg and n to the 2 dreg, where w is linear algebra constant. Oops, sorry. Well, moreover, since there is a block structure, actually you don't have to take all the variables to consider all monomials of a certain degree, but you can just consider certain of them, and actually the actual complexity would be n primes instead of n here to the power w direct. Okay, so some remarks. Well, there is a heuristic assumption here. I checked it for small parameters for random polynomials, but if you want to apply this analysis to other types of polynomials, you might have to check the assumption again. Okay, you can do the same analysis for other, let's say, small characteristic fields, and the general formula you would get is the following one. So for p equal 2, that's mt plus 1. Okay, so yeah, back to HFE. HFE is really a particular case of my analysis. So so the cryptanalysis leads to a particular case where m is equal to 1, so monovariate. T is log 2D, and the subspace is just the wall field. Okay. If you apply the analysis, you get Dirac approximately equal to DFF, which is bounded by mt plus 1. Sorry, it's minus. It's smaller here. Which is equal to log 2D plus 1. Okay. So we recover results that are well known for HFE, which is pretty well studied crypto systems. It seems that the spatial shape, like HFE polynomials, become quadratic when you apply the Veldesen. It seems that this spatial shape doesn't have too much influence. Well, it can have a positive impact, as shown in the paper by Dodges and Ding and Hodges in crypto last year. Okay, so other similarities with HFE, which I think are appealing, interesting, is that so yeah, it's kind of a polynomial system arising from a Veldesen. You have many low-degree equations, which was already observed a long time ago by Courtois for HFE. So the first full degree can be is the one I showed. Other arguments, you can like by applying different by modifying a little bit the system, you can get a subsystem with a smaller number of variables, which somehow also implies that the complexity is smaller, because yeah, complexity depends very much on number of variables. Okay, that was shown by Grenoble and Stern for HFE, and can be also extended to our general case. Well, and finally, the assumption Dirac is equal to DFF, or roughly equal, has been widely verified for HFE case. Okay, okay. So back to ECDLP. Okay, we're back to Dim's algorithm. Remember that we're working over the field f to the n. We have defined n prime and m such that m times n primes is roughly equal to n. We have defined vector basis as the set of points with x coordinates in a vector subspace here. Okay, and so relation search amounted to solve Siemens polynomial here with the additional constraints that the xj belong to the subspace. Okay, so that's what we want to solve. If we put that in together with our previous analysis, so you get sorry. By applying a Veldesen, you get a polynomial system again. The finite field is f2 to the n. You have a vector subspace of dimension n prime. There are m variables. The degree is, for similar polynomial, is 2 to the m minus 1. So in my analysis, I was assuming smaller than 2 to the t minus 1. So I have to take t equals to m here. And our analysis then leads to DFF smaller than mt plus 1 equal to m squared plus 1. It's not tight mainly because of this here, that I like bound the degree 2 to the n minus 1 by 2 to the m. Okay. Be careful that, okay, as I mentioned before, since summation polynomials are not random, you may have to check the assumption again. Okay. So here is, let's say, the same or different assumption. It's like a particular case. Let n and prime m e be fixed. Let r be a random parent of e. Let v be also random. We assume that when we apply a value system on the same-as polynomial, we get a system that satisfies this general heuristic assumption. Okay, so here is some data. Again, I couldn't go very far, as you see, and the largest n I got this is 17, and the larger n is actually 3. So if you bound 2 to the n minus 1 by 2 to the t, so t equal to m here, okay, and mt plus 1 with this would be that. So the values I observed in practice are actually smaller than that. I think it's just because this bound is not tight here. Okay. So that's data for random curves. You could also wonder whether Kubic curves are weaker or stronger, but well, I actually get pretty much the same results for Kubic curves here. Okay. So in both cases, it's interesting to note that not only the degree of regularity in practice was much smaller than generic systems, but it was even smaller than those bounds, right? Okay, so we have now all the ingredients towards like sub-exponential complexity. So again, in Deem's algorithm, the first step has complexity 2 to the t1, where t1 is roughly m squared. So finding the relations now, the total cost is 2 to the t2, where t2 has those 3 components. The n prime here is just because you need 2 to the n prime relations. That's the cost of solving one relation, right? By applying this Weberson technique, since each solution costs you n primes to the power w mt plus 1, where t is equal to m. Okay, so you get that. And the last term here is because you lost some factor because of the symmetry. Oops, sorry. And well, again, linear algebra is just that. Okay, so t1, t2, t3, and the overall complexity will be roughly 2 to the t, where t is the max of t1, t2, t3. Okay, so in this table, I computed for various n here. I chose various m. Then I deduce the corresponding n prime. I computed the corresponding t1, t2, t3, and the maximum of those. And then I kept in this table only the data for the m, such that t max was the lowest one. Okay. So for n equals to 50, this algorithm is not very efficient. Like it's much worse than even exhaustive search. For n roughly 160, well, you get close to exhaustive search, which is still not very interesting, right? And well, if you go up to n equals to 2000, then that's more or less where you cross with birthday attacks. So yeah, the sub-exponential complexity only starts becoming interesting here. Okay. Well, yeah, let's now come to this sub-exponential claim. So if we fix n prime equal to n to the alpha and m equal to n to the 1 minus alpha, such that the product is n, and we'll take alpha equal to 2/3. Okay, so back to our formulas. This is n squared, so roughly n to the 2/3. Here, the main component is this one, which is n to the 2/3 times, let's say, log n. And here the main component is this one, which is n to the 2/3 again. Okay, so here it is. We get that, that, and that. And then, sorry, the main term of all of those is really this one. So the complexity, the overall complexity can be estimated by 2 to the t, where t is equal to a constant c equal to 2/3 w. So c times n to the 2/3 log n, where c, as I said, is equal to 2/3 w, which is smaller than 2. All right. Here we are. Okay, so we're done. To conclude, I've shown some evidence that ECDLP over binary curves and more generally any small characteristic field curve, so that ECDLP could be sub-exponential. There is reasonable evidence in the heuristic assumption that's quite common, and that's supported by experience, at least for small parameters. Deem's algorithm, well, yeah, don't be afraid with your products. Deem's algorithm is still doesn't beat like burst researches like baby step, giant step, until you get for pretty large curve like n larger than 2000. Okay, so in particular, if you think of these curves, they're safe so far. So yeah, as I already mentioned, you can extend that analysis to any small characteristic field. Other point that I want to make is that polynomial systems arising from a veil descent seems to be very relevant to cryptography. I only saw ECDLP and briefly HFE, but as I said, you can also build an index calculus algorithm for f2 to the n with the same techniques. In that case, you will get complexity sub-exponential with this time exponent 1/2. So we're not quite as good as Coppersmith. And well, finally, some future works. Well, would like better algorithm. Would like to get rid of heuristic assumption as much as possible. And well, who knows? Maybe some extension to prime fields as well. But that's, I'm really not saying that that's possible. Just so bad. Okay. So thank you for your attention.
Thanks for your talk. Other questions?
Could you scroll back to the place where you were discussing the complexity of the complexity of the system solving, and given with in N and D reg? Oh.
The general case, or?
No. So there was a, you were discussing where the complexity is n to the d reg. Yeah. But this, so when d reg is not is much smaller than n, this is a decent approximation. But so, for example, if d reg grows to being proportional with n, I mean, this is not going to be. This is the wrong asymptotic, because the number of monomials is going to be exponential in n.
Well, I guess that's an upper bound, and well, it doesn't. Well, in my case, it's not like proportional to n, so it doesn't really matter, I guess. I guess that's an upper bound, right? Yeah. Yeah. So yeah, I'm not saying this is tight. It's just approximating number of monomials by n to the n, right? Yeah. And to the D-reg, yeah.